Okay, so what we're going to talk about today, you guys, is the solar system. And what I want to do here is cover everything. Should be pretty straightforward, but we're going to talk about the planets, how they got there, what was going on, how they were made, and then some particular interesting things about them. All right, so we're going to talk about beginning theories and current theories. So compare the different models and then talk about Kepler's laws. So geo means Earth. And so when we think about geocentric, it means centered around the Earth. And this was the philosophy 2,000 plus years ago that that the Earth was at the center of everything and everything went around there. Aristotle was the primary person who sent this idea forward, and pretty much that was the school of thought. But there was a problem, and the problem is if that was the case, and what they said was a number of the planets went around the sun, but then the sun went around the Earth, and so everybody was going around the Earth, and what happens is the planets did these giant burnouts in the middle of the sky, and so they called this retrograde motion. And a guy by the name of Ptolemy, the P here is silent, so you know what? These are called epicycles, and epicycles are these planets doing these big circles. And I've got this to show you on epicycles. Now, this is not what happens, but if you look, here's the sun, Mars, right? And then you have Venus, Mercury, and then at the center of it all is the Earth. And so I'm not going to play this out like this goes forever. And by the way, I want to make sure you guys know that the sound usually, the sound from these things is always like that violin music. Anyhow, so as I play this, what you'll see is here's Earth and the moon and Mercury and everything going around. So the moon's doing what it's supposed to be doing, but you see these little burnouts going on. And if we speed it up, whoops, if we speed it up, now we're speeding it up, right? And so time's going by, we'll take it down a little bit further. This would make an incredibly awesome tattoo. I was thinking about getting a tattoo. Just kidding, I'm not. Anyhow, what's happening is you see these little burnouts, right? This little, this little doop-de-doop. And so people couldn't explain that. And so he said, well, these are epicycles. And you got to think about, once somebody makes a claim, right? Everybody's like, oh, yeah. Until somebody else comes along and they said, okay, well, maybe that's not what's going on. And so these are epicycles, and I want to hit pause because I don't want to start in the middle of us here. Okay. And so if you look, this is what's happening in the sky and why. It's called retrograde motion. And so we have the sun here where it's supposed to be. Here comes Earth. And what you have is Earth is traveling faster than, like, say, Mars. This is Mars. And what happens is, and we're going to talk about what the Copernican or Copernicus system is, but what's happening is it looks like from the unaided eye is that Mars is doing this kind of loop-de-loop. And so they said, oh, it's doing an epicycle. And so all of a sudden, Copernicus comes along, and this is in the 1500s. Now, guys, what I want to point out here is that this is the stuff that would get you killed. I mean, literally get you killed. You say, oh, the Earth is not the center of stuff, and people would hit big rocks on your head and chuck them at you, right? And so this heliocentric model in the 1500s that Copernicus comes up with says, you know what, all the planets are revolving around the sun. Now, we know that's true, and that is what's going on. But it it wasn't well accepted until 100 years later when this dude by the name of Galileo Galilei comes along. Now, Galileo Galilei was really cool dude. He did a lot of stuff, but what does he do? He invents this device called the telescope. And by doing so, it brings the universe, it brings the solar system in close, and they can really do some monitoring of what's going on. And again, Copernicus never actually knew that his theory was correct because these two never ever met. But then comes a guy by the name of Johannes Kepler, and he was building upon the work of a guy by the name of Tycho Brahe or Tycho Brahe. And what they were doing is they were wanting to prove mathematically that planets followed a path called an ellipse. And so what is an ellipse? An ellipse is a circle that has two focuses or foci. And so in this case, our one focus would be the sun. Our other focus would be somewhere out in outer space. And we've talked about this, perihelion, where it is the closest to the sun, and aphelion is when it is furthest away. And the first law is basically that it's an ellipse. The second law, by the way, in order to do all this, we have to put everything into a unit called an astronomical unit. And I know we've talked about this before, but in order to deal with big distances, what scientists have done is they've said, okay, it's 93 million miles on average at the closest and furthest averaged out to the sun. And so we're going to call that 1. And by calling that 1, we're able to say, okay, how far is it? And so we're using that distance. The second part of Kepler's law is the law of equal areas. And what it says is that as a planet moves through its orbit, wherever it's at in the orbit, the areas are equal in the point of its period. And so it's really hard to state, but what I want to show you, equal areas. So all right, so this point to center in the focus, the area of this quasi-triangle is the same as the area of this triangle. And that's what the law of equal areas states. So if we take an equal time period, it takes the same amount of time to travel to here to here, to here to here, to here to here, to here to here, because the further away it gets, the slower it gets, right? And so the areas of these triangles, another cool design for a tattoo, by the way. Here we go. I'm not getting one, just saying. Right? So each of these areas are the same time. It takes the same amount of time to here, to here, to here, to here, to here, to here. And the areas of these are the same amount. And that's what the law of equal areas is. And this is the orbit of whatever planet or moon that is, law of equal areas. The law of periods. What does the law of periods do? It says that the radius cubed is equal to the period squared. Now I know you're going, what? It comes down to this, is the radius of the orbit is equal to, that's cubed, is equal to the period. All right, so again, law of periods, or Kepler's third law, basically is the orbit time and the radius. Radius cubed equals period squared. And Then comes Sir Isaac Newton, who applies it. And without Isaac Newton, without Kepler's laws, Newton wouldn't have been able to do what he does. All right, that is 29.1. Now we're going to get into the planets. And what I'd like to do is I've grouped them into the inner and the outer planets. The inner planets are what we refer to as the terrestrial planets. The terrestrial planets are Mercury, Venus, Earth, Mars. There's 4 of them, okay? And by the way, this morning at 5 o'clock, when you look, tomorrow morning it'll be the same place. When you look to the southwest, Venus is beautiful right now. It's coming up. So what I suggest you do is get up at 5 and take a look to the southeast, and you'll see it. All right, so the terrestrial planets, these guys are, and gals, are rocks. No rings, solid core. They've been beat to tar. In other words, we are constantly being impacted by objects from outer space. Start with the first one. By the way, this is a real picture, right? This is a satellite picture of Mercury. Mercury's orbit period, 88 days. It is rotating 59 days. So the length of a day there is 59 of our Earth days. No moons, no atmosphere. It's too close to the sun. And so on the lit side, it is 427 degrees Celsius. It's friggin' hot. But on the cold side, it's negative 173. Well, why is this so? Why does it cool off like that? Well, there's no atmosphere. And so because there's no atmosphere or very little atmosphere, it gets really, really hot and really, really cold. Very, very cool. You can see all the scars from being impacted, right? It's really cool. All right, Venus. Venus is the second planet out from the sun. Orbit period 225 days. It's almost the same size as Earth. It rotates very slowly, 243 days. So the length of the day on Venus is longer than the length of the year. I mean, I think that just boggles my mind. I think that's really cool. No moons again. It's really hot as well. 464 degrees Celsius. Very, very dense atmosphere. Why? The pressure. It also has carbon dioxide, and sulfuric acid atmosphere. What does that mean? Nothing will last there. However, it's very close to being the size of Earth. Earth, there you go. Mars is the 4th planet. And again, this is what I think is interesting about Mars. It has the same length, almost the same length of a day as Earth. It has a tilt. So we have seasons on Mars. The temperature is 20 degrees Celsius, which is about 60 degrees Fahrenheit, somewhere in there. And so can be a warm day, but 130, I think there's like 200 and something degrees Fahrenheit below zero. So it gets really, really cold, and it can be warm. Again, what are we looking at? Very little atmosphere. Olympus Mons, I think, is pretty cool. It's the largest volcano in our solar system. It's the size of Nebraska, and it's 3 times taller than Mount Everest. So it's really big. But it does have an orbit period that's twice as long as ours. Outer planets. These are the Jovian. Jovian means like Jupiter. This is Jupiter, and here's the Great Red Spot. Interestingly enough, I want to show you a video of Jupiter and the Great Red Spot. All right, so here's Jupiter, Great Red Spot. You can see the bands. The planet is spinning. So the bands are going opposite directions. And so we see this incredible display of these clouds and storms moving back and forth. Again, you can see the Great Red Spot right here. Some of the clouds are going this way, some of the clouds are going this way. We have this turbulent zone, and this is a hurricane type storm, only it's really, really large, like ginormous. Largest planet, orbit period's 12 years, rotates every 9.5 hours, or 9 hours and 50 minutes. It actually has more than 17 moons. We're always finding moons. Temperature, 30,000 degrees Celsius. It's hot. There's no rock here. This is a gas planet. In fact, these planets, we believe, are stars that just didn't form. Made of hydrogen, helium. Again, we see, as far as wind speeds, in excess of 540 kilometers per hour. Huge, 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 huge wind speeds. Here's Saturn. I think what's very interesting about Saturn, again, is obviously the rings. Rings are right here. It rotates every 10 hours and 30 minutes, negative 176 degrees Celsius, so it's probably like 300 degrees below zero. Orbit period, it takes 29 years to go around the sun. The question is what are the rings? The rings are ice. Uranus. Here's what's cool about Uranus. It's like a ball rolling around on the floor. Instead of spinning flat to a orbit, it's actually like it's rolling on the orbit parallel to the orbit. And so it's like you roll a ball. It also has rings. And what's interesting is, why is it blue? Well, Uranus is blue because it has methane and hydrogen and helium in its atmosphere. Methane, when you heat it up and look at it, it is blue. And so, is there water? We think there could be. But again, it is one of those planets that's the same, very hot, lots of dense pressure. With pressure comes heat. It has a lot of moons as well. Smaller, we're getting smaller in size compared to the others. Again, it's the third largest planet, so Jupiter, Saturn, and then Uranus, but we're starting to get smaller. Neptune has also a big storm, the Great Blue Spot. We've got some serious wind speeds, 1,000+ kilometers per hour. Surface temperature is very cold, negative 225 degrees Celsius. This is negative 300, maybe 400 degrees below zero. Very similar in size to Uranus, so it's a bigger planet. But its orbit period, it's way out there, 164 years to go around. It rotates every 16 hours. It also has rings. And then there's our little one, Pluto. Pluto has been downgraded to a planetoid. It used to be a planet discovered by Clyde Tombaugh in the 1920s or 30s, somewhere in there. Clyde Tombaugh is Streator, Illinois, obviously. And so what has happened is, because it doesn't act right, it's too small. It's a planetoid. It rotates every 6 days. Its orbit period's way out there. Now here's something that's cool. It sometimes switches orbit with Neptune. And so it's sometimes the 8th and sometimes the 9th object out there. Notice I said object, I didn't say planet. Again, methane, rock, ice. This is a rocky planet. Temperature is very, very cold, negative 300+ degrees Celsius. Has a moon, has a large moon called Sharon, named after Ozzy Osbourne's wife. Actually, Sharon! Actually, it's not. It's spelled differently. Anyhow, why is it not a planet anymore? It just doesn't act right, and it's too small. So there's our little Pluto planetoid. All right, so we're going to go ahead and stop there. Thank you so much. You guys are awesome, and keep on working hard.